Prisoner's Dilemma. Probably the most famous game, and the one that I first learned about, goes something like this. You have prisoner 1, and you have prisoner 2. Your matrix looks something like this, okay? You have two options. You can either think, which means to tattle, or you can stay quiet about the crime that you've committed, okay? So I'm gonna put F here and F here for think or to tell, and I'm gonna put Q here and Q here to stay quiet. If both prisoners stay quiet, their payoff is 1, okay? If player 2 thinks and player 1 stays quiet, then player 2 is perceived as the less hardened criminal. So their payoff is their payoff is 2, better payoff, and player 1 gets a payoff of 0. Okay? If they both tell on each other, 0.5, 0.5. Okay? So what's the Nash equilibrium? Well, let's think about it. If I'm player 1 and I stay quiet, player 2's incentive is to think. If I'm player 1 and I think, player 2's incentive is to think as well, because 0.5 is higher than 0, okay? If player 2 stays quiet, well then I want to think, and if player 2 thinks, then I want to think, okay? So there's only one Nash equilibrium, which is fun. The NE is at think. So both players tell on each other, okay? And that's interesting because this is usually the first game you get shown, and your instinct is to say QQ because everybody gets a higher payoff by 0.5. But it's not right because either player only cares about their own incentives, their own personal gains. So let's take another example and try to make it look as close to the prisoner's dilemma as possible. Okay, so I'm going to write the rules down and then we're going to figure this out. Okay, so in this situation, we're telling a story about fish. So we have fish that can change their sex depending on how likely it is for them to find a mate. So if there's a lot of males, then they have the incentive to become female, and if there's lots of females, then there's more incentive to change into males. But say that there's two fish that have the same preference, and both of these fish are considering mating with each other, okay? But since they are both the same sex, there needs to be some sort of compromise, right? Either one will have to change, or one won't, or they could both randomize, in which this is the case. If both decide to mate in either role, then it randomizes and you get the average of both options, okay? So we're asked to create a game that looks exactly like the prisoner's dilemma, but now with fish trying to babies, okay? So clearly more important. I love fish. So let's get started. This game is in the textbook, An Introduction to Game Theory. I highly recommend. This is the last time I'm going to say it in a video, guys. This is the last time I'm going to say it. Please read it. Okay. So there's oh my God. There's two states. There's two states here that we need to think about. There's compromise, and then there's sticking with their guns, getting what they prefer, really, okay? Okay. We have BBAA, where we have plan B and plan A. Plan B is compromising, plan A is not, okay? So, when both fish are unable to compromise, they both want to stick to plan A, it's SS, okay? So where S is when they go off and search for another partner because either fish is not able to compromise, okay? And then BB is when they do this thing. So both fish so when they both compromise, they get the average of H plus L, where H is greater than L, okay? When fish number 1 gets what they want and fish number 2 is compromising, then fish 1 gets H, fish 2 gets L, and for B and A, it's LH, okay? So you're already kind of seeing what's going to happen here. Because if fish 1 is compromising, then it's always in fish 2's best interest to not compromise. It's always better for them to go for their plan A. So in this case, when fish 1 is willing to compromise, fish 2 is going to say, no, I'm going to go for what I want. I'm going to go for plan A, okay? When fish 1 is going with what he wants, this is where the fun really starts. We need to assume something. We need to assume that S is greater than L. We need to assume that S is greater than L. However, S is smaller than the average of H plus L. And I'm going to explain why this is the case, okay? Because then in this story, fish 2 is going to want S instead of L because S is greater than L, okay? Also, we need to assume that S is smaller than H, okay? So S is bigger than L, smaller than H, and smaller than the average of H and L, okay? Right, so back to what I was saying. Fish number 1 is attacking. Fish number 2, or not attacking. Fish number 1 is going with plan A. Fish number 2 is going to go S, okay? And when fish number 2 compromises, it's in fish 1's best interest to do H because H is greater than the average of H plus L, obviously, because L is less than H. And then when fish 2 goes for plan A, it's in fish's 1 best interest to go S. And we have the exact same situation where it would have been better for either fish to just compromise. It would have been better for either fish to just compromise instead of both the fish going off and finding separate mates because that's taking them more energy and time. However, every single time one of them would have compromised, the other one would have went for their higher utility. So it's not a Nash equilibrium. But we need, for this story to make any sense, we need to observe these rules as true. We need to assume that S is in fact greater than L, so it is chosen in both cases. When either fish is choosing between S and L, we need to assume that S is less than H, okay? And we need to assume that S is also less than the average of H and L, okay? So maybe we want to give, let's do this just for practice, because technically we've answered this. We've made this game look just like the prisoner's dilemma, but let's make it look even better, okay? Okay, so if you wanted to visualize this with actual numbers, you could assume that S equals 1, so let S equal 1. You could assume that H equals 3, and you could assume that L equals 0, okay? This makes perfect sense for our rules. In this case, 1 is greater than 0, 1 is certainly less than 3, and 1 is also less than 3 plus 0, okay? Because, well, guys, I know I shouldn't have to do this, but I feel like I should. This is equal to 1.5, okay? So therefore, S is smaller than 1.5 because S is 1. So we have given S, H, and L actual values. I didn't put the values in here because I was running out of room. I just wanted to explain it over here. And anyway, but this game mimics a very similar story to our prisoner's dilemma. Okay? And I hope that makes sense to everybody. Okay, thank you for watching.